Hi everybody, Mrs. Pesic here. We're looking at Chapter 5, Analytic Trigonometry. Section 5.1 is using fundamental identities. So the fundamental identities are located on page 348 in your book, and you are going to need to copy them down onto index cards, and these must be memorized. So that's why I want you to basically make flashcards for yourself. So if one of the trig identities, for example, is sine of theta equals 1 over cosecant of theta, I want this to be the front of your card, your index card, and this to be the back of your index card. All right, so again, you're making little flashcards for yourself, so you can just flip that back and front and learn to memorize these trig identities. All right. For the trig identity, that's sine squared theta plus cosine squared theta equals 1. I really want you to make 3 flashcards out of this one. I want the front to be, on one of them, to be sine squared plus cosine squared of theta, like that. And the back would just say 1. And then front, that's the back. But I do want you to get 2 more identities out of this same identity right here. So for example, if we subtract sine squared from both sides of the equation, you'll have a new identity that will be helpful to you, and that will be cosine squared theta equals 1 minus sine squared theta. So again, I want another index card here, and the front will say cosine squared theta, and on the back it'll say 1 minus sine squared theta. Likewise, if instead of subtracting sine squared from both sides, you subtract cosine squared from both sides, then the cosine squared subtract off, and you will have the identity that sine squared equals 1 minus cosine squared. So you'll have sine squared on the front and 1 minus cosine squared on the back. All right, so you're going to make 3 index cards, 3 flashcards for each of the Pythagorean identities, but every other identity you just need 1 flashcard. All right? Okay, so let's get started. You're going to be referring to, what page was that? Page 348 while we're watching this video. So page 348 until you have your index cards made. All right, so it says if sine of x equals 1/2 and cosine of x is greater than 0, use trig identities to find the values of all 6 trig functions. All right, so for this example, this is the first one on your gift, okay? It says sine of x is 1/2 and cosine of x is greater than 0, and you're supposed to use your identities. Well, we have the identity that says that I can find cosine, right, from the identity that cosine squared is equal to 1 minus sine squared, right? That's going to be one of the identities. You're making a flashcard, right, like this. So I can just plug in my sine value. So I get 1 minus 1/2 quantity squared. I'm plugging in sine. I'm plugging in the 1/2 for sine, but of course I've got to square it. So that's supposed to equal cosine squared theta. So I get 1 minus 1/4 is cosine squared theta, and so that means I get cosine squared theta equaling 3/4. I do need to take the square root of both sides, and you know that means I need a plus or minus. Very important here. So I get cosine of theta is equal to plus or minus square root of 3 over square root of 4. But of course, square root of 4 is really just 2. So I get plus or minus square root of 3 over 2. But they did give us a little bit more information. They said cosine of x is actually greater than 0. So that means I know that I don't need the negative, and my answer is really going to be cosine of theta is equal to square root of 3 over 2. All right, so there's my first one. We already know what sine is. Now we know what cosine is. So if we want to find tangent, we could use the identity that says tangent of theta equals sine of theta over cosine of theta. All right, and if we do that and we plug in our values that we know that sine is equal to 1/2, and the cosine we just found to be square root of 3 over 2. So simplifying this, I get 1/2 times 2 over square root of 3. The 2's divide out. I get 1 over square root of 3. and I can multiply this by square root of 3 over square root of 3, and I get square root of 3 over 3 as my answer for the tangent of theta. All right, so tangent of theta equals square root of 3 over 3. All right, so far we have three trig values, and there's just 3 trig values left to go. And those are all the reciprocals. So if I know that sine of theta is 1/2, then the cosecant of theta is 1 over the sine of theta. So cosecant of theta is going to be 1 over 1/2, which is equal to 2. So now we know cosecant of theta is equal to 2. Likewise, if I know that the cosine of theta is square root of 3 over 2, then the secant of theta is 1 over the cosine of theta. And so I get secant of theta equals 2 over square root of 3. And I could multiply by square root of 3 over square root of 3 and get 2 square root of 3 over 3. So that's getting 1 over the cosine. I just flipped the cosine value. Last one is the cotangent of theta, and that is 1 over the tangent of theta. So that means I really just need 1 over square root of 3 over 3. And so in that case, I can say 1 times 3 over square root of 3. And if I multiply by square root of 3 over square root of 3, I get 3 square root of 3 over square root of 9. That's 3 square root of 3 over 3. The 3's divide out, and I'm left with just square root of 3. So I get that the cotangent of theta is equal to square root of 3. I think we found all 6 trig functions. All right, let's take a look at example 2. This one is asking you to simplify the cosine, simplify this expression, cosine squared x times cosecant x minus cosecant x. In this section, the name of the game is to be able to, rewrite expressions using, using trig identities. We're going to recognize and write the fundamental trig identities, and we're going to use those fundamental trig identities to, simplify expressions. So in this case, I think that we could simplify this if we notice that this is one term and this is another term. And this kind of harkens back to the appendix where we factored things, because I see we've got a common factor here of cosecant of x. So if I factor that out from both, then I'll be left with cosine squared of x minus 1, right? Because cosecant x times cosine squared x would get me to this first box, and then cosecant x times a negative 1 would get me to that second box. All right, and notice here I have cosecant x, and then really if I see cosine squared, I know from my identities and from my flashcards that that's equivalent to 1 minus sine squared, right? We agreed we were going to make one of our flashcards look like cosine squared on one side and 1 minus sine squared on the other. And then I still have this minus 1 here, but in this case, the 1 here and the 1 here are going to subtract off. So I get cosecant x times a negative sine x. All right? And really, cosecant x is the same as 1 over sine x. So I get 1 over sine x times a negative sine x, or you could think of that as negative sine x over 1. And it looks like I can just divide out the sine x's, and I'm left with just negative 1 as my answer. All right. So that's how we could simplify in example 2. All right, let's take a look at example 3. It says factor 1 minus cosine squared. We're trying to factor that. It doesn't look like there's any common factors, but in this case, we could factor it thinking of a difference of 2 perfect squares, because that's 1 is a perfect square, and cosine squared is also a perfect square, and there is subtraction in between. So it's kind of like factoring, x squared minus 16 factors into x plus 4 times x minus 4. So that means that this will factor into 1 plus cosine x times 1 minus cosine x. Again, we're using our difference of 2 perfect squares factoring. So this would be our answer for this problem. All right, let's take a look at example 4. So we're factoring 2 cosecant squared x minus 7 cosecant x plus 6. I don't see any common factors to factor out here, but I do notice that this cosecant, this term has cosecant squared, this one has a cosecant to the first, and this one is just a constant term. Well, that kind of reminds me of factoring like a 2x squared minus 7x plus 6. And you are all experts at that. We could use product sum, right? The product sum technique might work for this guy as well. So if we do this, we could say, oh, my product is 2 times 6, product is 12, and my sum is a negative 7. So I think the two numbers that we would want would be what? Negative 4 and a negative 3, right? They multiply together, give me 12, and they add up to negative 7. So let's do that, except instead of with x's, let's do that with cosecant x's. So in this case, we want to take out the negative 7 cosecant squared, and we're going to replace it with a negative 4 we're taking out the negative 7 cosecant x and replacing it with negative 4 cosecant x minus 3 cosecant x. So altogether, we're going to write 2 cosecant squared x minus 4 cosecant x minus 3 cosecant x plus 6. Factoring by grouping, which you are all experts at. What could I factor out of these first two? I think a 2 and a cosecant x. And then what's going to be left would be cosecant x minus 2. And then what can I factor out of these two? I think I can only factor out like a minus 3. And if I factor out a minus 3, I'll get cosecant x minus 2. Because the negative 3 times the cosecant x gives me this term, and the negative 3 times the negative 2 gives me the plus 6. So I think the idea here is that we see the same expression in both of these, so we could factor that out and get cosecant x minus 2 times 2 cosecant x minus 3. All right? And factoring like this, it's not just a fun thing to do, it's going to be helpful for us when we are solving trig equations in section 5.3. But for right now, we are just simplifying expressions, not solving equations. Let's take a look at number 5. We want to factor this. We're trying to factor secant squared x plus 3 tangent x plus 1. Problem. We see two different trig functions, so we're going to need to use one of our Pythagorean identities, and I see that we have an identity that's 1 plus tangent squared equals secant squared. 1 plus tangent squared equals secant squared. And so in this case, I think I would replace this secant squared right here with 1 plus tangent squared x. If we do that, then we're going to be left with only one trig function in this expression instead of two. And so if I combine the ones here, I get tangent squared x plus 3 tangent x plus 2. Again, I would use product sum. My product is going to be 1 times 2, which gives me a product of 2, and the sum is this middle term along with the sign is 3. So I think that my numbers would just be a 2 and a 1. So I think I would just take out this 3 tangent x and replace it with a 2 tangent x plus a 1 tangent x. And so we're going to have tangent squared x plus 2 tangent x plus 1 tangent x plus 2. Factoring by grouping, I think I could factor out tangent x, and then I'll be left with a tangent x plus 2. And then what can I factor out of this? Nothing, except 1 or negative 1. I'm going to factor out a positive 1, and I'll be left with tangent of x plus 2. But good news, the parentheses match, so I can factor this into tangent x plus 1 times tangent x plus 2. And we're done. All right, that factor's completely there, or that's as far as we can go with this. Okay, let's take a look at example 6. This one says cosecant x minus cosine x times cotangent x. And for this one, I mean, it may be helpful to rewrite everything in terms of sine and cosine. So if we try that, we know cosecant is really 1 over sine x. I'm using my identities. And then I get minus cosine x. Well, I could think of that as cosine x over 1. And then cotangent x is cosine x over sine x. All right? And with that, looks like I have 1 over sine x minus, I guess, cosine squared x over sine x, right? If I multiply my numerators together and I multiply my denominators together, right, because I'm multiplying these two fractions. Good news, we have a common denominator here of the sine squared x is here and here. So I could really write this as 1 fraction, 1 over cosine squared x over sine x. All right, and that's looking pretty good, but don't we know what 1 minus cosine squared is? Isn't that one of our identities? One of the things you're going to put on your flashcard, and I think that is just sine squared x now over sine x. And really, sine squared is really sine x times sine x, and that's over the sine x. So I think it's certainly okay to divide out one of these sines with one of these, because the sine x is being multiplied, it's a factor, and so that means we really just end up with sine x. So this expression right here is just a fancy way of writing sine of x, right? So that's it for that example. Let's take a look at number 7. In this case, we're supposed to perform the addition and simplify. So in this case, this time we don't have common denominators, so we can't just add them right now. We have to get common denominators. Good thing we did the appendix, and you guys are all experts at adding rational expressions where you have to get a common denominator. I think the common denominator here, I'm going to write up here, the least common denominator, I think is going to be 1 plus sine theta times 1 minus sine theta. So I think that means I need to multiply this fraction by 1 minus sine theta over 1 minus sine theta. Hopefully the appendix is all coming back to you. And likewise, I think I'd have to multiply this fraction by 1 plus sine theta over 1 plus sine theta. All right, in this case, my first fraction is going to be 1 minus sine theta over this common denominator. And then my second fraction, here's my big plus sign there, and then my second fraction is going to be 1 plus sine theta over 1 minus sine theta times 1 plus sine theta, our common denominator. Okay, so now I have a common denominator, so now I can combine my numerators and get 1 minus sine theta plus 1 plus sine theta, and that's all over my common denominator of 1 minus sine theta times 1 plus sine theta. All right, well, it's looking pretty good, but I think we can clean it up a little bit. Sure looks like the sine theta here and this sine theta are going to subtract off, and so I think we're going to have 2 over the 1 minus sine theta times 1 plus sine theta. All right, I think we could rewrite that denominator as 1 minus, let's see, if we did FOIL on this, we'd have a 1, we'd have a plus sine theta, then we'd have a minus sine theta, and then a minus sine squared. So I think the sine thetas would subtract off, so I think we have just 1 minus sine squared theta. But that's a flashcard, right? You're making that into a flashcard, and that's really cosine squared of theta. Okay, and I think the last thing we could do here is to rewrite cosine squared. Since that's in the denominator, we could write that as 1 over secant squared theta, again, using another identity. And then that's the same as 2 times the reciprocal. So it's 2 times secant squared theta over 1. And so we get 2 times secant squared theta as our, I think, our simplest way of writing this expression. So again, I think this expression here, our original one here, right, is really just a fancy way of writing 2 secant squared theta. All right, let's take a look at number 8. This one says rewrite so that the expression is not in fractional form. So let's say we didn't want a fraction. Well, I would think that what we could do is rewrite, using an identity, rewrite cosine squared y. What's our flashcard say about that? That that's really the same as 1 minus sine squared y. And so I have that over 1 minus sine y. So can I divide out, one of these signs with this sign? That would be a big no-no, because the sine y in both places are really terms, and we're only allowed to divide out factors. So this is no good. Let's get that off the table here. But I think we can recognize, and we already factored one like this, that this numerator could be factored because it's a difference of two perfect squares. So that means I could really write it as 1 plus sine y times 1 minus sine y. Again, it's kind of like, factoring x squared minus 9 into x plus 3 times x plus 3. Whoops, x plus 3 times x minus 3. Okay, and so don't forget, though, that we still have this denominator of 1 minus sine y. Is it okay to divide out this 1 minus sine y here with this 1 minus sine y? That's a yes, because this 1 minus sine y up here in the numerator is a factor. It's being multiplied by everything else in the numerator. So I think our final simplified form for this would just be 1 minus sine y. All right, let's take a look at number 9. It says simplify, and we're trying to simplify cotangent squared over cosecant squared. In this case, cotangents and cosecants go together pretty nicely, and so for this one, I think that we may, actually, you know what, instead of, let's see, I think what I would suggest on this one is let's rewrite everything in terms of sines and cosines. So that means I could really write cotangent squared as cosine squared theta over sine squared theta, right? That's how I would rewrite cotangent squared. And then the cosecant squared is the same as 1 over sine squared theta. So I could write that one like that. And then since I'm dividing by a fraction, that's the same as multiplying by the reciprocal. So I could rewrite this as, cosine squared theta over sine squared theta times the reciprocal, which is sine squared theta over 1. So I'm being a little, kind of sneaky about this, but then the sine squared thetas will divide out, and it means we're just left with cosine squared theta as our simplified answer. All right, that's it. Thanks for watching this video. Have a great day.